Hello and welcome to this session on Introduction to Distributed Systems. Before moving into what exactly are the distributed systems, let us see the objectives set out for our discussion today. So we start our session with the introduction to the multiprocessing systems. Then we know something about the processor coupling and types of processor coupling, distributed systems, definition and its features. And then we will see design goals of the distributed systems and what are the issues that are involved in the distributed systems while designing the DOS. So let us start with the multiprocessing systems. What are multiprocessing systems? Multiprocessing systems is a general term for the use of two or more CPUs. Within the word itself, we are having multiprocessing. Multiprocessing is nothing but whenever we are talking about multiprogramming, it involves many programs. Whenever we are talking about the multiprocessing, it involves more processors. And then it may be giving an idea about the processes also. Like multiprocessing means it may be giving an idea of multiprocesses also. Like whenever we call a program in an execution is a process. So then we can take the depending upon the context, even we can interpret that particular multiprocessing as a multiple processes handled by the CPU as a multiprocessing concept. In the later on the session, let us visualize the difference between the multiprocessing capability and the multiprocesses handled by the CPU. So this particular multiprocessing, whenever we are defining, it involves many processors, many CPUs attached with the system. And then multiprocessors can vary with context mostly as a function of how the CPUs are defined. Whether the CPUs are lying on the same board or within the same system, or else many CPUs are logically connected and are being interpreted as a single system. So this is there are different contexts where in which this particular multiprocessing can be varied. Then the term multiprocessing is sometimes used to refer to the execution of multiple concurrent software processes handled by a system or handled by a CPU. So this particular concept exactly doesn't fit in the multiprocessing, but we can call that particular concept as the multiprogramming. This is nothing but whenever there are many programs or else many processes handled by a single CPU existing in the system, we can always interpret that particular definition as a multiprogramming. So where lies the difference? So suppose if a system consists of several processors, like there are two CPUs in the same system connected by a bus. So there may be a possibility of multiprocessing as well as multiprogramming done by that system, or else only one of the two, either of the two is possible, or else neither of the two is also possible. Then we will see the processor coupling. So we are talking about the multiple processors lying in the system. So how these particular processors are connected? This particular connection, interconnection of the processors or some sort of logical connection of the processors is called as processor coupling. So multiprocessor is nothing but two or more CPUs logically connected. Either it may be lying on the same board or in the same system, or else it is being distributed in various systems, and that particular integration we call it as call that one as a multiprocessing event. So multiprocess systems have more than one processing unit sharing memory or peripheral devices. They have greater computing power and higher reliability. So these are the key goals or else key features of the multiprocessing system. Suppose if you take the case of uniprocessor system, it can handle multiple tasks or else concurrent tasks at the same time. But those particular tasks are being handled by a single CPU. So one process is allocated to the CPU, it executes, then it will, whenever there is some sort of request by the process, either it may be a hardware request, it may be a resource request, or it may be any other printing request done by that particular process, then that particular CPU leaves the process and once again another process is being attached or allocated to the CPU. Meanwhile, the first process is being fulfilled by the request, like resource sharing or something like that. So here the uniprocessor, or else only one processor, one CPU in the system, is completely taking care of all the processes that are there in the RAM. But in the multiple processors, there may be several programs handled by several CPUs. That is the major difference. Then there may be several memories also. Suppose for example, if a multiprocessor system is consisting of 4 nodes, and that particular 4 nodes are combinedly called as one system, integrated system, under some multiprocessing operating, some distributed operating system, it has been handled. Then that particular system is n exponentially powered with computing, and then there lies some high reliability also attached with that system. So multiprocessor systems are not uniquely classified, but there are 2 types of multiprocessor systems. One is loosely coupled system and the other is tightly coupled system. So what are tightly coupled systems? Tightly coupled systems are nothing but each processor is assigned a specific duty, but processors work in close association, possibly sharing one memory module. So it is nothing but you can view that this particular system is having mostly 2 or more CPUs are existing in the same system. Suppose if you take the case of only one system existing in your lab, and it is been called as a tightly coupled system, means that particular system is having 2 or more processes within the system, and the memory may be same, or else memory may be same, and also the other resources may also be the same for that particular system. But the difference is that it is not no more a uniprocessor system but a multiprocessor system. And the tightly coupled multiprocessor systems contains multiple CPUs that are connected at the bus level. So this is the basic difference between the tightly coupled system and the loosely coupled system. What I am going to say is, in this particular tightly coupled system, in the same system, you will be having different processors lying on the board, but those particular CPUs are connected through a system bus, through a bus level architecture. And then these CPUs may have access to a central shared memory called as SMP, or many participate in a memory hierarchy, one with the local and other with the shared memory. So there may be existing one local memory for each and every processor attached with, or else there may be a centrally only one memory shared by different processors existing in the same system. So there are 2 types of things. Then the example for this particular tightly coupled system is IBM P690 Regatta. This is the example for the tightly coupled system. This IBM P690 is nothing but the mainframe system. So mainframe systems with multiple processors are often called as the tightly coupled systems. Then comes the tightly coupled systems perform better and are physically smaller than loosely coupled systems. Why? Because as I am saying that whatever the processor number may be, either it may be 2 or more processors, those particular processors or CPUs will be lying within the same system. So obviously the size will be very much reduced, and it may be looking like a small desktop, but have historically required greater initial investments and may depreciate rapidly. Depreciate rapidly is nothing but, why we are saying is, for every 6 months, in the present situation, we are encountering a new configuration of CPU. Earlier it is a dual core, right now we are talking about the quad core. So for every 6 months, the configuration of the CPU is changing. So suppose if we are purchasing a system right now, means obviously after 6 months the value of that particular system will automatically depreciate as the new processor come into the market. And the tightly coupled system tend to be much more energy efficient than the clusters. Here the clusters are nothing but the loosely coupled systems. This is due to fact that considerable economies can be realized by designing components to work together from the beginning in the tightly coupled systems. In this way we can compensate the depreciation value with respect to the months that is been aging. So in this way we can try to depreciate the economies in the tightly coupled systems. Then comes the loosely coupled systems. Loosely coupled systems are nothing but, these are the autonomous computers. Loosely coupled multiprocessor systems often referred as a clusters are based on multiple standalone single or dual processor commodity computers interconnected via a high speed communication system. So this is the difference between the tightly coupled and the loosely coupled. In the tightly coupled system, everything we can see it as a one system with number of processors lying on the board connected by the bus architecture. But in the loosely coupled system, there are several computers, there are several clusters. We can call each and every node as a cluster, each and every computer, autonomous computer as a cluster, and then those particular clusters or those particular nodes are connected via through a high speed communication system. So suppose if there are there are 4 systems, if there are 4 nodes, and if we want to call that particular thing as a distributed system, so those particular CPUs are connected through some operating system called as distributed operating system, and then the communication between each processor will be done by the high speed communication system like a network, high speed network. Then the example for this loosely coupled system is Linux Beowulf. This is the example for the loosely coupled system. This particular Linux Beowulf, there are several scalabilities. It may range from 2 to 4 or 4 to higher level scalability also. That is nothing but 2 computers may be called as one distributed system, or 4 computers integratedly called as one distributed system, or if the scale rate is very high, that particular number of clusters, number of nodes are called as one single distributed system. Then these nodes, whatever we are calling the autonomous computer, in a loosely coupled system are usually inexpensive computer and can be recycled as independent machines upon the retirement from the cluster. Suppose if you have a distributed system connected via loosely coupled, and there are 5 autonomous computers connected to that particular loosely coupled system. Suppose if you want to have only 4 systems right now, and then earlier it was 5. Suppose the 5th system, whatever that we are trying to delete from that particular architecture, we can deconnect that particular system, and we can use obviously just like a PC. So in that way, no system may be going waste. And then the loosely coupled systems are not much energy efficient when compared to the tightly coupled system. Why? Because whenever we are talking about the tightly coupled system, that itself is an individual system with number of processors connected by the bus level, bus system architecture. But whenever we are talking about the loosely coupled, there are several nodes attached with the system. So each and every node will be consuming some sort of energy. So whenever we are comparing this particular loosely coupled system with the tightly coupled systems, then these are not much energy efficient. Then let us see how these particular systems are being handled by the multiprocessor operating system. So whenever there are several systems, like loosely coupled systems needs to be handled as an integrated system, then there should be some sort of controller, or else a manager, or else a resource manager should be available in order to control all the systems, like which process needs to be given which CPU, or which process needs to be thrown to which node. So that particular handling mechanism is being provided by the multiprocessor operating system. So what is exactly the multiprocessor system? Look into the slide. Multiprocessor operating system aim to support high performance through multiple CPUs. This is the basic feature. Then an important goal is to make the number of CPUs transparent to the application. Here transparency is nothing but you are submitting, you are looking the whole thing, loosely coupled system, into a single system. Suppose if it is a tightly coupled system, then also the same things, the same view. From the user point of view, it is only a single system. We are submitting the job, and then it is the operating system which will distribute the work to different CPUs. There the user's participation is nil, but the participation of the operating systems comes into picture. So it is the job of the operating system, like which part of the process or which part of the program is to be diverted to which node or which CPU. That is the major job by the multiprocessor operating system. So here in the multiprocessor system, multiprocessor operating system, there lies the the hurdle wherein which it has to control different programs. Suppose if each and every program in execution will be having certain processes and even sub-processes also. So that particular processes, sub-processes are to be handled by not single CPU but various CPUs attached. It may be 2 or more. So the job by the multiprocessor operating system when compared to the single user operating system grows exponentially. Then achieving that particular such transparency. Transparency, what I am telling you is, transparency is nothing but the user may not be in a position to know that which chunk of the program or which chunk of the process is being executed by which node, that he may not be in a position to know, but the operating system will be knowing, and then the operating system will be pooling in such a way that whenever one of the CPU sits idle, immediately the process that is lying in the queue is being thrown out to that particular CPU for execution. And then from the user's point of view, it is only like one system handling the job. But from the operating system point of view, it is nothing but it is handling several processes associated with the several programs by various CPUs. So that is the hidden feature of the multiprocessor operating system. Then the idea is that all communication is done by manipulating data at shared memory locations, and that we only have to protect that data against simultaneous access. So suppose if we are thinking that there is only one program, and that program can be executed parallelly. Like suppose if one processor is executing one part of the program, one part of the process. So suppose if that process, the second process is not dependent on the first process. So obviously the second process can be diverted to another CPU so that both the processes run simultaneously, because there is no dependency between the process 1 and the process 2. So both of the things can be run parallelly by two different CPUs. So whenever there is certain data to be shared by the processes, then that particular data is being shared using the shared memory concept. That is nothing but many programs, they will be using the same memory location, and whenever one updates, the updated thing will be taken by the second one. So in that way, the memory will be shared by various processes which are being executed by various CPUs. Then protection is done through synchronization primitives like semaphores, as we had learned earlier, and the monitors. So these are the two mechanisms by which the shared memory or the simultaneous execution of simultaneous access of the memory is being controlled. And then suppose if one CPU wants to talk to the other CPU, like if there are two CPUs, they want to talk, or else they want to send some communication. So that particular communication will be sent through the messages only. Communication is possible only through messages by various CPUs. And then let us see what exactly is the distributed computing. So this particular whenever I am talking about the distributed systems, these distributed systems comes under the loosely coupled systems. Distributed computing is the process of aggregating the power of several computing entities to collaboratively run a computational task in a transparent and coherent way so that it appears as a single centralized system. So this is the basic goal of the distributed computing. So suppose if you take the case of several loosely coupled systems, several systems attached to a loosely coupled system, and then the user will be submitting his job, then that particular job is being distributed to various CPUs. So here what we are getting is we are aggregating the power of each and every CPU. Suppose if there are 3 CPUs attached to that particular loosely coupled system, what we are trying to say is the power we are utilizing is not from the one CPU or single processor, uniprocessor, but we are trying to aggregate the power of 3 CPUs. So that is nothing but we are, when compared to the uniprocessor system, obviously the high performance rate is growing by 3 times. Then the distributed computer system is a loosely coupled collection of autonomous computers connected by a network using system software to produce a single integrated computing environment. In the tightly coupled system, there is no problem. It is only one system, but there are several CPUs lying with the same system. But in the loosely coupled system, there are several CPUs in the form of different computers, like in the form of different nodes, and those particular nodes are to be controlled by the distributed operating system, and the job whatever the user will submit is nothing but it will be distributing the job to the various CPUs attached to that system. Then we will see what are the properties of these distributed systems. The basic goal we had learnt is aggregating the power of several computing entities to collaboratively run a computational task in a transparent way. So how this particular thing can be achieved? So let us see the properties of these distributed systems. Distributed computing consists of a network, if more or less independent or autonomous nodes. So this is nothing but a loosely coupled system, and the nodes do not share primary storage or secondary storage. So this is also one of the difference between the tightly coupled system and the loosely coupled system. Whenever we are talking about the loosely coupled system, we are talking about the nodes. Those nodes are connected by high performance network. So whenever we are trying to focus on a node is nothing but it is a individual autonomous computer. Individual autonomous computer means which will be having its memory, local memory, and that particular local memory is not shared by each and every computer, each and every node in that particular distributed system. So each and every computer, each and every node will be having one fixed memory, or else the secondary storage, like the secondary storage in the sense the hard disk. So each and every autonomous computer will be having a CPU, one or more CPUs, and then the memory of its own, which is not shareable by other nodes, and then we will have that system will be having the secondary storage of its own. Then a well-designed distributed system does not crash if a node goes down. Suppose if in a distributed system, if there are 5 nodes connected to that particular system, and if one goes down, like one crashes, the user has submitted the job and he is waiting for the result. So meanwhile, one of the system crashed. Even then, the system won't fail, but it will continue its processing job by using the other 4 systems integratedly. So that is the charm of the distributed system. Then if you are to perform a computing task which is parallel in nature, scaling your system is lot cheaper by adding extra nodes compared to getting faster with a single machine. Suppose if you have the tightly coupled system, you will be directly submitting the job to that particular system, and that particular job will be handled by the various CPUs existing in that system only. Suppose if you take the case of loosely coupled systems, so there are several nodes, and then suppose if you want to scale that system to 5, suppose if the existing strength of the loosely coupled system is 5 nodes, suppose if you want to scale, if there is a big job, and if you want to scale the system, then you may go for 7 systems, another 2 nodes attached to that system, and a little bit of configuration is needed that you can do, and obviously you can scale up. And there will be certain limitations, like the capacity may be not limited like 10 or something like that, but that particular factor we have to keep in mind. Otherwise you can scale the systems by adding the nodes to it. Suppose if you want to delete the nodes, then obviously you can delete the nodes, or else you can remove the nodes, then you can use that particular system as an individual computer. So there won't be any problem to that particular distributed system. Of course, if you are processing tasks in highly non-parallel, suppose if there are parallel tasks, those can be submitted to the various CPUs and can be executed in the distributed systems. Suppose if the program whatever we are submitting, user is submitting, is of non-parallel kind, like the process 1 is the process 2, whenever we tries to execute, the complete outcome whatever the process 1 is taking, that may be the input for the process 2. So in that way, in that situation, what the processor has to do is, there is nothing like it has to wait till the process 1 complete, and then process 1 output is available to the process 2. Then only the process 2 will be started. So suppose if the program itself is in the non-parallel fashion, most probably, or else this particular distributed system may not be that much used in that context. The network connections using the system software is the key feature. So whenever we are talking about the loosely coupled systems, the only way that we can connect those particular nodes is nothing but through high performance network. So remote access requires explicitly message passing between the nodes. Node here is nothing but an autonomous computer. So whenever we are trying to access, suppose if I want to, if there are 5 systems and one of the system, if I call some A4 and I am sitting on A1, suppose if I want to communicate or if I want to remotely access that particular A4, the only thing that I can do is through message passing only I can access that particular node. And even in the, whenever we are looking the distributed system, that too loosely coupled distributed systems, most probably the way the remote access is we can, the remote access will be very much slow when compared to the normal thing whenever while working with the networking software, networking operating system software. Then messages from CPU to CPU are possible, and then protocols are designed for reliability, flow control, failure detection, etc. implemented in the software. So whenever we are talking about the networks, there should be some sort of protocols which will be dealing about the reliability and the flow control. Flow control here is nothing but the process control. So suppose if the user is submitting the job, then it is the part of the operating system, distributed operating system, that it should judge which part of the process should be given to which CPU. That is nothing but it is trying to divert the process, the part of the process to one of the CPUs, maybe CPU 1, CPU 2 or CPU 3. And it is the job of the operating system that it has to save the other parameters, and then it has to look after the control rate of the process. Then it, if at all some sort of requirements are there, it should fulfill. And then it is the control of the, it is the job of the operating system that once the process is already executed, then it has to take up the task and it should be integrated in such a way to give the result. Then mode of communication between the nodes is by sending and receiving the messages through the network. So this is the only possible way that one CPU, one autonomous computer or one node with one CPU tries to communicate with the other CPU which is there in the other autonomous computer. So let us see the basic difference between the distributed operating system and the network operating system. Here we are talking about a system with different autonomous computers connected, and transparency is the key feature in the distributed operating system. But in the network operating system, each and every system will be having its own operating system. Let us see the differences. In the distributed operating system, the machines supporting a distributed operating system are all running under a single operating system that spans the network. So here, even though we have 5 nodes attached to that particular distributed system, the whole control will be with only one distributed operating system. But in case of network operating system, each machine runs an entire operating system, an entire network operating system. So each and every computer on a network operating system, each and every operating system will be having its own entire piece of network operating systems on the machines, and then they will be exchanging the messages between the nodes. But in case of distributed operating systems, there will be only one distributed operating systems controlling all the loosely coupled systems. So there lies the difference. But that particular distributed operating system spans all over the network. Suppose if there are 5 nodes connected, means it will be spanning the whole 5 systems and it will be controlling. Then the print, let us see the example. The print spooler might at some instance be running on one machine, while the file system is running on the other node, and while other machines are running other processing, but the whole control will be under one distributed operating system. But in contrast, with distributed operating systems, the entire system is itself distributed across the network. That is the basic feature of the distributed operating system. Then we will see the advantages of a distributed system over the centralized system. Suppose let us see there is a centralized system with centralized system in the sense that there are certain servers and clients attached with that particular, clients are attached with that particular servers. And once when we are sending the request, and the requests are being accepted by the servers, and depending upon the request, the responses are being sent. Like in the, what are the basic differences between, basic advantages that we are gaining in the distributed systems when compared with the centralized systems? The first feature is, as we are talking, the better price performance than the mainframes. And the second feature is more computing power. We are getting more computing power when compared with the centralized system. Some applications are inherently distributed. Some applications means, suppose if there are several parallel tasks that are there in the software itself, design software itself, then inherently that it obviously supports the distributed mechanism. Then improved reliability because system can survive crash of one processor. Crash of one processor in the sense crash of one node. Suppose if there are 5 nodes attached in the system, one of the node gets down, like crashed. Even then the system survives and it can execute that process with other 4 processors, and then it can give the result. It does not hamper one. If one processor goes down or else crash, it means it does not hamper the activity or it does not hamper the processing power. Then incremental growth can be achieved by adding one processor at a time. This is nothing but whenever we are trying to scale the system, we can obviously add the system and we have to configure certain parameters. Then shared ownership is facilitated. And then we will see the advantages of these distributed systems over the isolated PCs. So shared utilization of resources. This is possible with the distributed systems. Communication is the key feature. As all the loosely coupled systems are attached with a high performance network, obviously the communication feature, communication between the CPUs is the unique feature that we have in the distributed system. Then comes the better performance and flexibility than isolated PCs. That obviously we agree. Then simpler maintenance if compared with individual PCs. Suppose if individual PC goes down, means the whole system is of no use. Once the system is once again we repair, then only that particular system, with that particular system we can execute the task. Suppose in case of distributed system, if one goes down, if one node goes down, even then also we can work with the other nodes. Then let us see the disadvantages of the distributed systems. Even though we have very key features like advantages with the distributed systems, it suffers with some sort of disadvantages also. Let us see one by one. The first feature is network performance parameters. So whenever we are whenever we want to have higher performance in case of multi-processors, that in the loosely coupled systems, the network parameters plays the major role. So we have to set the parameters in such a way that it should give the efficient performance. Then the latency is a basic disadvantage. The delay that occurs after a send operation is executed. Suppose if there are 5 systems attached in the distributed system, and then suppose if one of the system is throwing some message to the server, then after sending that particular message and the response time, suppose if it is asking for some sort of data, the time that is between the sent operation and the receiving operation, that particular time obviously is countable. Like delay that occurs after a send operation is executed before data starts to arrive at the destination computer. Whenever there is a node requesting for the data to be sent, that particular request, from that particular time onwards, the time counts, and that particular time after receiving of the data at that particular node is called, the delay time is called as the latency time. That should be very much minimal in nature, otherwise it is a disadvantageous factor. Then comes the data transfer rate, speed at which the data can be transferred between 2 computers once the transmission has begun. This particular data transfer rate also should be very low, otherwise it will be one of the disadvantageous factor. Then comes the bandwidth. Whenever we are talking about the bandwidth, then comes the volume of traffic that is to be handled by the network, that comes into picture. So once the bandwidth is very much high, then all the operations or else all the communication part will be taking very less time. Then it will be in the advantageous state. Otherwise, suppose if you have a distributed system with some 100 nodes and the total network is filled up and there is a kind of congestion in the network and the bandwidth is very low, obviously the system performance will be degraded, and then there will be a high, the process performance factor will always be at the lesser side. Then comes dependency on reliability of the underlying network. Whenever we are talking about the high speed network attached to the nodes, suppose that particular network architecture also plays the topology or the architecture also plays the role. Suppose if it is not fitting, if it is not fitting in the scene, then it may be hampering the things also. Like it may be causing some sort of problem to the systems, some sort of problem to the nodes. So that particular thing should be taken care by taking the consideration of the topology or the architecture that is to be provided. Then high security risk due to more possible access points for the intruders and possible communication with insecure systems. So whenever we are talking about the network, the security plays the major role. The hamper or else the intruder can be looking for the vulnerabilities in order to provide some sort of threat to the network. So those particular things can be overcome by providing some sort of network security software. Then comes the software complexity. Whenever there is this particular software complexity is nothing but it pertains to the distributed operating system, that is the system software. Because suppose if you are for the first instance, if we are scaled to only 3 computers and those particular 3 computers are being handled by the distributing operating system, it may be it will be giving some sort of fruitful results. Suppose if the system is being scaled to several computers, like from 3 to some 7, 8, 10 or something like that, then it is the pressure on the distributed operating system which needs to be controlled. So there lies then whenever we are trying to configure those nodes also with this system, there lies some sort of complexity attached with the distributed operating system. Then after looking these particular advantages, disadvantages, let us see what are the goals. What are the goals while designing the distributed systems? So these are the goals these are the 6 goals that we have to see, design goals that we have to see whenever there is a design of the distributed operating system. In order to design a good distributed system, there are 6 key goals. One is the concurrency, then scalability, openness, fault tolerance, privacy and authentication, and then transparency. Concurrency is nothing but a server must handle many clients. So one system in the distributed system, one system will be the server and the other system may be clients for some instance. Then suppose if a server, if a request is coming from the client, the server should handle the clients. And distributed systems are naturally concurrent. That is the basic key feature of the distributed systems. So concurrency, whenever we are talking about the concurrency, means it is having multiple workstations running multiple processes independently and even at the same time. So concurrency is important because any distributed service that is not concurrent would become a bottleneck and that would serialize the actions of its clients and then reduce the natural concurrency of the system. So in this particular context, concurrency will play the major role in the distributed system. Whenever we are talking about the distributed system, means altogether the concurrency concept is involved in it. Suppose if there is no concurrency concept, then there won't be any parallel executions and there may be some sort of serial executions. For that particular serial executions, no need of going for the distributed system, but we may go for the serializable systems. Then the next one is the scalability. So whenever we are designing the distributed system, means we have to see the scalability factor also. So whenever we are designing the distributed system, means for the first instance it may be having only some few nodes like 1 to n nodes, but we have to have certain vision also so that it can accommodate several nodes like n plus 1, n plus 2, n plus 3, n plus n nodes. Even that particular n also should have some sort of limitation, not as much as we can do. That particular n plus something nodes can also be accommodated whenever there is a scalability factor. So this particular, whenever we are designing the system, distributed system, means obviously the vision should be very much higher. Then comes the openness. Openness, in the sense there are 2 types of opennesses. One is non-proprietary and then the other is the extensibility. Non-proprietary is nothing but, whenever we are talking about the distributed system, obviously the communication is through the network. So suppose if whatever the network software that we are selecting, the network architecture whatever we are selecting, suppose if it is of proprietary kind, Then whenever we are trying to expand, or whenever we are trying to scale, or whenever we are trying to configure something else, then obviously we have to have certain patches also. So those particular patches also we have to take it from the proprietary vendor or else proprietary company wherever we had bought the networking software. Suppose if we we go for the open source software, then whenever there is a sign of expanding, or whenever there is a sign of inclusion of some sort of public protocols, then the patches are also may be available upon the request on the by the open source vendor or open source the websites. So from there we can download, we can use that particular protocol as and when we are as and when the system requires. Then comes the extensibility factor. Extensibility factor is nothing but it is important because it aids the scalability to talk to each other. So we are extending, and whenever we are trying to extending, that is nothing but whenever we are trying to scale, obviously the other nodes, whenever we are trying to scale, those also should respond. Those particular nodes also should give proper responses and should be included in the system and should obviously habitate with the system. They should not act a peculiar kind of thing, or they should not be shut down immediately. So those systems also brought into the integrated fashion, and then those can also be used. Then comes the fault tolerance. Fault tolerance is nothing but it is critically that a distributed system be able to tolerate the partial failures. Partial failures are of two types, like failures are more harmful, that we will know. But whenever many clients are affected by the failure, obviously in the distributed service, obviously it hampers the system performance. Like failures are more likely, but those particular failures are to be visualized, anticipated, and then the solutions are also should be provided in such a way that it can provide some sort of fault tolerance mechanism. Then there should be some sort of privacy and authentication also. Privacy is achieved when the sender of a message can control what other programs can read the message, and client's authentication is needed to enable a concept called as trust concept, and the server's authentication is needed to enforce some sort of access control mechanism. Then transparency, this is the basic thing, basic key feature of the distributed systems. So these are the 6 basic design goals whenever we are trying, the people are going for the distributed operating system. So I hope that you had understood the introductory concepts of the distributed operating system. In the next session, we will look into the sharing concepts, and then how the inter-process communication and synchronization of the CPUs, various CPUs will be possible in the distributed systems. With this, I conclude the session. Thank you.